we are discussing about lateral directional dynamic stability, and in particular we are trying to find out if there is a simplified way of understanding this phenomena which would help designers to initially freeze some design parameters. That is the basic requirement. We have discussed about longitudinal dynamic stability. We have assumed that disturbances are small and even the steady state angle of attack are small, or we are talking about small angle of attack. We also assume the rates are also small. Why? For simple reason, if rates are very high in the longitudinal plane, if angle of attack is very high, then this longitudinal disturbance dynamics will also have an effect on the lateral or directional dynamics. Since we have assumed small angle of attack, small perturbation, we have assumed that longitudinal dynamics is decoupled from lateral directional case. But now when we are talking about lateral directional case, we understand lateral means if this is the airplane, this is the x-axis, this is y, this is z. Lateral means we are talking about motion about x-axis, roll or bank, and directional is motion about z-axis, yaw, right? Okay. But one thing you should understand that lateral and directional case, they cannot be decoupled generally. That is, you can understand if suppose this is the directional case, that is right wing is going back, what will happen? As right wing goes back, this left wing will come forward, so the relative air speed of the left wing will increase, hence the lift will increase, so it will bank also. So there is a coupling between directional and lateral case. So reverse will be there. If there is a lateral disturbance, there will be a directional influence on the whole airplane dynamics. That is why we need to go with lateral directional case together. We are not decoupling lateral and directional case. Although we will see some approximate studies where only we assume lateral dynamics and directional dynamics separately also yield some useful information, especially for the designers, right? And our approach was first to write the equations of motion, which already we have derived, now introduce perturbation, and then follow the similar steps as we have done for longitudinal case. So we will take one equation and we will try to revisit, and we will see that you are very comfortable. Nothing extra we are doing here as far as technique is concerned. If I take equations along y, force equation along y, so along y direction, force equation, then rolling moment about x, yawing moment about z, these three, that is this motion, and this motion. That is, if you see like this motion along y, roll about x, and yaw about z, right? So I will take first y equation, and if you recall, the equation was of the form mv dot plus ur, let me write this, w1 into p is equal to mg sine theta 1 plus theta 1, or I don't write 1, mg sine theta, let me check it, m v dot plus u r minus wp, I don't put 1 here now at this point, this is the general equation, wp equal to mg sine phi cos theta. So this is wrong, mg sine phi cos of theta plus fay, and you can always write fty. Let me check again on the right hand side, it is mg sine phi, yes, cos theta, correct, fay, this is fine. This is the equation of motion along y direction, right? What was v? V was the component of total velocity along local y direction. That is, If this is the airplane, this is the x, this is the y, this is the z, and this is the total velocity vt or v star, whatever you write, then if this v is the component of this velocity resolved along y direction of the body fixed axis system. Right. Now, next step was introduce perturbation. So, we introduce perturbation. What we have to do? V will be equal to V1 plus small v. All small quantities are perturbed quantities, but they are small perturbation. Then U equal to U1 plus small u, R equal to R1 plus small r, then W equal to W1 plus small w, P equal to P1 plus small p. Similarly, you could see phi equal to phi1 plus small phi, theta equal to theta1 plus small theta, then fay is equal to fay1 plus fay. I am neglecting the thrust component. We are neglecting it with the understanding that we know how to handle this if I know how to handle fay term. What was fay? Ay is the perturbed aerodynamic force along y direction. And also we know at steady state what is true is m v1 dot plus u1 r1 minus w1 p1 is equal to mg sine of phi 1 plus phi, then cos of theta 1 plus theta plus fay1 plus fay. Okay? And also we know that we are assuming theta, phi, all are small, such that sine of theta is approximately theta, sine of phi approximately phi, and cos of theta goes to 1, cos of phi goes to 1. Nothing new we are doing. Right? So what we will do, we will expand this the way we did it for longitudinal case. We will substitute this conditions and then simplify. And if I give you one more step to just recall what we have done, what you have to do for the first equation, you write m v1 plus v dot, then plus u1 plus small u into r1 plus small r minus w1 plus small w into p1 plus small p. This is equal to mg sine of phi 1 plus small phi into cos of theta 1 plus theta plus fay1 plus fay. You could easily see this, which you have seen for longitudinal case also. Since at steady state this is true, this can be easily taken out from here. M v1 dot, then u1 r1, w1 p1. Similarly, and expand this sin phi as sin a plus b cos a plus b. Expand it, put this approximation, and when you do all this thing, you will get an equation. So you know that as we have done for longitudinal case, you have to expand it, take out the term because they are automatically satisfied, use this approximation, and also note, this is nothing new I am doing, also note at steady state V1 we have taken as 0, cruise, phi 1 equal to 0, P1 equal to Q1 equal to R1 equal to psi 1 dot equal to theta 1 dot equal to phi 1 dot, all are equal to 0. We are talking about cruise, steady, level, unaccelerated flight. So this also goes to 0, and now when you put all this thing here, you get very simplified equations of the form. So when I do all those substitution, then I get the equation in the y direction, the perturbed equations of motion as mv dot plus u1r minus w1p is equal to mg phi cos theta 1 plus fay cos theta 1. What is theta 1? Is the attitude of the airplane during the cruise. So that need not be 0. Okay? That's why you have kept the theta 1 so far. And also note here, the moment I put another condition that we are using stability axis, and recall what is stability axis? If this is the airplane, and this is the normal body x, y, and z, and let's say this is the relative air speed, and this is the angle of attack, then xs means that x-axis is aligned with the velocity vector in the vertical plane, and this becomes zs. The advantage is if this is xs and this is zs, then naturally w1 is 0. So we further simplify this equation and we remove this term. So we get this equal to this in stability axis system. Okay. So now the equation becomes much simpler. So I write this equal to this. And we should be careful that we are now using stability axis system. The moment I use stability axis system, please understand, earlier this Ix's, Ixz were about this x, y, and this z axis. Now you are solving everything in stability axis system. So this Ix's, Ixz, Izz, Ixz, they also should be in stability axis system. So Ixs, Ixz, Izz, all these should be in stability system. What mathematically it means? That you know the moment of inertia about x, y, z axis. This is one axis transformation with alpha. So you have to calculate the new values of moment of inertia about stability axis system, and for that you can directly use transformation, which I will just give for completion. This is Ix x stability axis, Izz stability axis, Ixz stability axis. This will be cos square alpha 1 sine square alpha 1 minus sine square alpha 1, then sine square alpha 1 cos square alpha 1 sine square alpha 1 and half sine 2 alpha 1 minus half sine 2 alpha 1 and cos 2 alpha 1 into Ixx body axis, Izz body axis, Ixz body axis. Okay. This you can check any literature. How do I do body axis transformation? That is, if this is x, y, and z, then how the values which are measured with respect to x, how can we transform them about another axis which is rotated by angle alpha. Right? You can please cross check this. Okay, the important part what you should understand, when I am using this stability axis system, how much this moment of inertia is going to change, because it's an angular motion, lateral directional, right? Two motion, one is roll, one is yaw, angular motion. How they are getting affected? So we need to have some numbers with us to get some feel for numbers. And for completion again, I am giving you some sort of an influence matrix where you can easily understand how much it will happen. If it is alpha 0 degree and 5 degree, I take two cases. If Ixxb is 10,000 in some unit, then alpha 0 it is 10,000. For 5 degree it becomes 9751 Similarly, IZZB, if it is 23,000, and it becomes 23,249. Oh, sorry, for 0 degree it is even same, 23,000. For this it becomes 23,249. Similarly, IXZB, if it is 2,000, it remains 2,000, of course, alpha 0, but here it becomes 841. So it is not really to be ignored, because a lot of cross coupling happens through IXZB, and then all this are showing a lot of influence. Okay, so that's why as a designer we need to have this feel how much percentage these values will change, right, before you comment on the final result. Okay, if this is true, and if we have understood up to this point, let me erase this. Now what was done? Remember, this is FAY, LA and NA, they are to be expanded in terms of motion variable and control variable, and we have already seen that this can be written as, say, FAY, I can easily write as half rho V square S into CYP into PB by 2U1, let's say, plus CYR into R B by 2U1, CY beta into beta, CY delta A into delta A, plus CY delta R into delta R. We have seen this, how to write this. Now, if I substitute this here and then divide by M, then I can write this equation in a dimensional derivative form, which we did for longitudinal case, and that would be V dot plus U1 into R equal to G, M will get cancelled, G phi cos theta 1 plus Y beta into beta, or let's don't write Y beta, we write YP into P plus YR into R plus Y beta into beta plus Y delta A into delta A plus Y delta R into delta R. Are you clear what we have done? We know this expansion, we have seen, because FAY, what is FAY? FAY is half rho V square S into CY. And what is CY? CY is half rho V square S. CY is CY function of P, R, beta, delta A, delta R. And assuming aerodynamics to be linear, we have expanded this as CYP into PB by 2U1, and PB by 2U1, you know B by 2U1 we have multiplied to non-dimensionalize P, all the rates, right. So this is the form the equations are taking, and if you want to see yourself what will be the value of Y beta, you could see from here Y beta will be what? Instead of Fy, I will write this expression divided by M. So beta, 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 beta is here. So that will be half rho V square S Cy beta divided by M. You see, this is half rho V square S Cy beta by M, but we know that. We'll evaluate this at steady state, so Y beta will be written as dynamic pressure Q1, this at steady state S Cy beta by M. Similarly, if you want to check what will be the expression for Yp, it is very simple. Come here, we are actually putting this expression here. So P is here, this is half rho V square S Cyp into B by 2U1 divided by M. So Yp will be Q1 S B Cy by 2M U1. Isn't it? Check yourself here. If I take this term, this is half rho U1 square, because evaluating at steady state, into Cyp into Pb by 2U1. So this will be divided by M, because I am writing in terms of V dot. This is V dot is here, so M will divide both sides. So what will happen here is, I can see this, I can write as yp into p. So what is yp? Half rho u1 square, which is q1. q1 is here, s is here, this b remains here, b, cy is there, cyp, not cy, cyp. This 2 is here, this 2 is here, m is here, u1 is here, so e1 is here. Okay? Right? So that becomes your yp. Similarly, you can check other dimensional derivatives. And if you do the similar exercise for lateral and directional case, then you will get equation of the form. Let me write this complete. V dot plus u1 r is equal to g phi cos theta 1 plus yp into p plus y r into r plus y beta into beta plus y delta a into delta a plus y delta r into delta r. Similarly, from the second equation, you will get p dot minus a1 r dot equal to L beta into beta plus L, or let me write LP into P, same sequence, LR into R plus L beta into beta plus L delta A into delta A plus L delta R into delta R. And A1 is nothing but IXZ by IXX. Let me write B1 also here as IXZ by IZZ. And third equation, we will get R dot minus B1 P dot is equal to NP into P plus NR into R plus N beta into beta plus N delta A into delta A plus N delta R into delta R. You will get these three equations, and this will represent short period equation of motion for lateral dynamic case. Okay? And you have seen that we have made the aerodynamic model fairly simple. We have not talked about beta dot. There could be delta R dot also, but we are taking a simple case. Okay? I am sure you will be, once you know how to do this, you will be able to do this second and third equations. What is important for you to know, what are the expression for LP, LR, L beta, so that you can cross check yourself by doing it. So let me write those. LP is Q1 SB square CLP by 2IXX U1, that is LP. LR is Q1 SB square CLR by 2 IXS U1. Then your L delta A will be Q1. Let me write this as B CL delta A by IXS. And then if you see L delta R will be Q1 SB CL delta R by IXS. Then N beta will be equal to Q1 SB. Very simple, you could see that by IZZ. Then NP will be Q1 SB square CNP by 2IZZ U1. Then NR will be Q1 SB square CNR by 2IZZ U1. You can find out N delta A and etc. What I will do, I will be giving page on the whole this expression. You need not remember this, even you need not remember these equations. I'm again and again telling you. These are standard ones you have to do to make clear-cut understanding what are these things. Okay? So now, once you have this, then what is the next step? Next step is, this is in time domain. We understand if I solve this in time domain, I should be able to track the values of small v, r, p to comment on the dynamic stability of the machine. But we will be following the Laplace transform approach. We will work in the frequency domain in S plane, so that these differential equations become linear algebraic equations, right? So that will be our next step, and then we will find matrix, then we will find the characteristic roots, as similar way as we have done for longitudinal case, right? So I like to stop here so that you at least digest this. Please remember one thing, no need to remember, no need to cram anything here, okay? Only you understand, if somebody tells you n beta, what should come to your mind? Cn beta. What is Cn beta? Cn beta is directional stability. Cn beta should be greater than 0. Np, you should think what is Cnp. Nr, you should think of Cnr. All these derivatives I have explained to the sign and etc. last lecture. That is more important. As a designer, you should have that in your mind, so that you know if you want to increase n beta, how to increase Cn beta, whether I increase vertical tail, whether I take the CG backward, or I put something with the wing, or make the fuselage a little differently. That is what is required from this expression. Okay? Thank you very much.